All right, so let's go over the exam problems we had, and hopefully this is going to be helpful for you guys to understand better of these, and hopefully it's going to be helpful for your finals as well. And first problem, this thing is something we tried in class. So the mass, we have two blocks like that, and this is like 25 kilogram, and this is 15 kilogram, and we have this block that is sliding towards block A, and then once they have that impact, then they're going to be connected, so it's going to be a single big chunk, and that's going to compress the spring we have here, right? So it's like a two-part problem, as I explained in class. So we have this impact, right? And then once they become a single particle, this is just pushing the spring. So you want to consider this impulse, and you want to consider this spring and some object compressing it. Okay. So determine the velocities of the block right after the impact. And here we can use that MV, conservation of linear momentum. So MAVA1 plus MBVB1 is going to be MAVA2 plus MBVB2, right? And this is what? It is before that impact, and this is right after that impact. Okay? And one thing that we can note is VA2 is going to be same as VB2, because after impact they're going to be combined as a single particle. So the velocity of this guy and the velocity of B, they're basically going to be the same, right? So we can call this thing, let's just make it simple, let's just call it V, to make it simple for notations. And we can try to solve this thing. VA1, this guy has a value of 0, right, because it is at rest. And VB1, this one we need to consider, we can, if we set our axis going to this direction as my positive, then this is going to have a value of plus or minus the velocity here. If I consider going to the left as a positive direction, and this is going to the left, so we're just going to use positive 15 meter per second here. Or the opposite case, if I just consider going to the right as my positive direction, then this has to have a value of what? Minus 15 in there. Okay? So I've seen a few of you made a little bit of mistake about those, so I just wanted to make sure about that. Okay? So here, just to be simple, we will consider going to the left as my positive, and this is going to have a positive 15 velocity. So here we're considering positive 15 in there, right? And this value, MA has 25, and MB is what? It's a 15, and these are basically the same, 25 and 15. So it's going to be 25 times 0 plus 15 times 15 is going to be 25V plus 15V, right? So here this is 225, and this is 0, and it's 40, so 225 is equal to 40V, and if my math was correct, we get 5.625 meter per second like that, and it is a positive value, therefore it is going to the left. Okay, so this is the velocity of this big chunk right after they collide to each other. Okay, then the next one, determine the coefficient of restitution between blocks A and B. What's this? This one, I consider this almost like a bonus problem, and you really don't need to do any math. It's just basically zero, because that's a plastic impact. You have both of those, colliding and become a single particle, then there's no separation velocity between them, right? So it's just basically zero. Or if you wanted to do that math, you can try V of B, V of A, V of A, V of B, and then these are 2, and these are 1, and you subtract those, right? That's how I explained in class. These has a subscript of 2 because this is after, right? And these down here have a subscript of 1 because this is before, right? And you want to have these A's and A's and B's and B's across from each other, something like that. And if you plug in these numbers, well, this one, A has a velocity of 0 and B has a velocity of 5, and these two have the same velocity, so it's 5.625 minus 5.625. So it's minus 5, 0 over minus 5. Okay, so it's pretty straightforward if you knew the concept here. Okay, and then let's move on here. Determine the max compression of the spring, and this thing we can try using the energy principle, right? Energy conservation. So T1 plus V1 is T2 plus V2. This is right after impact, and this is when it has max compression, right? So in this situation, there's no potential energy, and when it's max compressed, it means it stops, so the velocity is going to be 0, so there's no kinetic energy. Therefore, here it's just 1/2 mv squared. That's going to be same as 1/2 k delta squared. So what's that? It's 1/2 m was 40 because total, this big chunk is moving, so that's going to be total 40 kilogram, and the velocity we obtained was 5.625 squared, right? That's going to be 1/2 k is given as 10 kilonewtons, so 10 kilo, we have 3 more zeros there, and that delta squared, right? So half goes away, and if you do a little bit of math, this should give us something like 0.356 meter. Okay? All right. Any questions up to here? All right, not. Let's move on. And then this problem was actually coming from the homeworks. So let's try. It's 5 kilogram block pendulum shown in the figure, originally at rest, right? And when a 2-gram bullet strikes and becomes embedded, then the block swings to its max, which has an angle of 5 degrees. So when the bullet hits here, and then this guy will boom swing up, and this is going to have a degree of 5 degree angle. And gravitational acceleration, g, is 9.8 meter per second squared here, and then we want to find these. So first we want to find the speed of the bullet right before it hits the block, right? And then we want to find the coefficient of restitution between the block and the bullet. What's this first? This is going to be 0 as well, right? Because it becomes embedded and becomes a single particle, right? So there's no separation between those two. So here you can answer this in 1 second if you knew that concept here, right? Because it becomes embedded. It's a single particle. And then next, let's try to find this the speed of the bullet here. And because we have two particles, it has mv1. Let's call the bullet A and the block as B. So MAVA1 plus MBVB1 is MAVA2 plus MBVB2, right? And in this situation, we all again we know that MVA2 is velocity VB2 because they are becoming a single particle. And this guy, let's just call it V to make it simple. So I'll just make it like that. Okay? And from here, we can solve this thing. Let's say this guy is 2 grams, so it's 0.002 kilogram, right? And velocity, I don't know. And this guy, how heavy is that? Is that given?
The block?
Yes. Oh yeah, it's up there, 5 kilograms. And the velocity, initially, this is 0, right? So what we have is 0.002 VA1 plus 0 is the summation of these two, 5.002 V. So we have this equation ready. So in order to find this guy, if we know V, then we can solve it, right? And that one, this V, we can find it from the case where these two become a single part and it is swinging up to its max, right? And here we can use that energy principle one more time, because 1/2 mv squared is going to be same as mgh. Get it? This thing has an initial velocity of v, and then it is swinging up to its max height, so it is going up by that h. So if we solve this one, or to be more precise, v1 is t2 plus v2, and the initial case, we don't have any, we don't have any potential energy. In the latter case, we don't have any kinetic energy, so this is going to be same as that. All right, so from here, m basically goes away, so it's 1/2 v squared is 9.8 times h, and we need to find that h. So h can be obtained by doing a little bit of geometry. So we have this thing swinging up like that, right? And from here to there, it's going up by this h. And this angle, we have that theta. So this length was what? It is 1.25 meter. So it's 1.25 total. This length is 1.25 as well. So if we just try to find this length, that's going to be what? 1.25 and cosine theta, isn't it? So the h we're looking for is going to be 1.25 minus 1.25 cosine theta. And it is given the theta was 15 degree. It's 5, so this is going to be 5 degree. Okay, so if we plug this number in here, h, like that, then v is going to be 2 times 9.8 times that h, 1.25 minus 1.25 cosine 5 degree, right? And you can just put a square root like that. And if my math was correct, we get, what do I get? I think I get like 0.3. And if we plug the velocity in here, we will be able to find VA1, which was the velocity of the bullet. And that is going to be something really big, something like 763 meter per second. Okay? Does that make sense? So initially we have something very fast moving like that, and it's super light, only like 2 grams. And once it gets embedded to this heavy stuff, that is swinging up slightly. All right? And when it gets embedded, this guy was fast, but it's super light, so the combined velocity is going to be pretty small, like only 0.3 meter per second in this situation. Okay? Any questions up to here? Okay, it's not. Let's move on. And then this one here, the link AB, this guy has a velocity of omega AB, and that's 5 radian per second, and at the instant of theta was 45 degree, we want to determine these things. So determine the velocity of point B, right, both magnitude and direction, and determine the instantaneous center of zero velocity and show it on the figure, and we want to determine the velocity of block C. So this one here first, the velocity there is pretty straightforward. It's going to move in this direction, isn't it? Perpendicular to that swing. All right? So let's call it VB. Therefore, VB, let's move it down here. VB is going to be what? Omega R. And omega here, it was given as 5 radian per second, and the R is 0.5. So it's 2.5 meter per second. And it has an angle here of 45 degree. Okay? Does that make sense? And then the next question here was to determine the instantaneous center of zero velocity and show it on the figure. So the way, again, this one I was a little bit surprised because I thought this is almost like a free, easy problem to solve, but more than just a few of you guys didn't do it correctly, or even not show this thing on the figure. So here we have a velocity like that, and at this point we have a velocity like this, right? Or maybe it's going to the right, but anyway, it's moving in this direction. So what we can do is we can draw a perpendicular line against that velocity like that, and against this velocity draw a perpendicular line like that, and here is going to be my instantaneous center of zero velocity, and we assume at that moment this guy is having a pure rotation about this point. So of course the velocity is going to be in that direction because it's moving like this. Okay, so given this thing, now we can find the velocity of block C. So let's call it VC. And let's call this omega VC again. Then VB is omega BC times RB, and VC is omega BC times RC. RB, I mean, is this length, and RC, I mean, is this length, right? It is just having a pure rotation, and you have a length or arm like that, and you have an arm like this. So from here, we know that 2.5 is omega BC times that RB, which we don't know, but we can find that thing doing a little bit of geometry. This is a 45-degree right angle triangle, right? So this is 1.5, so this is going to be 1.5, and this is going to be 1.5 square root 2, right? So this is going to be omega BC times 1.5 square root 2. So from here, we can find out omega BC is, it has a certain value, something like 1.18 radian per second. And of course, it is rotating like that. And we can utilize this thing in here with that RC, which is 1.5. So 1.18 times 1.5, and that should give us something like 1.77 meter per second. And of course, it is going to the left side.
Would you take off credit if you got that answer when we did it a different way?
No, if you did it correctly, then we're all good. Okay, if you use that relative motion analysis, that's fine. Okay, does that make sense? Any questions up to here? So, just to stress one more time, if you have a particle or a rigid body, okay, and if you know the velocities at different points, like for example, here it has a velocity going in this direction, and here it has a velocity like that, then you will want to draw a perpendicular line against that velocity at each point. So at this point, like that, okay? And then where they meet is going to be the IC. And with respect to this point, it's having a pure rotation. So this whole thing is rotating like that. It's rotating like this around here. So finding the velocity becomes a little bit straightforward. It's just omega r. Okay? Then you should be able to find these things a little bit more in an easy way. Okay? All right. And let's move on. And the next problem was about this collision. So this is something we tried in class, just the numbers were slightly updated. So we have two identical frictionless balls, and they are colliding each other with an angle shown there, and right before the collision, there's this yellow and green had a velocity of 3 and 5, like that. So we can write it. This has 3. Red color. This is 3 meter per second. This is 5 meter per second, like that. And that E value is restitution coefficient is going to be 0.9, and coordinate system is in that direction. And here we would like to find the horizontal and vertical velocities of these before the collision. So all we had to do was just do a little bit of geometry. Like that. This is 3, and this is 5, and this is 30 degree, and this was 60 degree. And we have the axis like X and Y like that. So if we call this one A, and if we call this guy B, VA X1 is going to be 3 times cosine 30 degree, right? VA Y1 is going to be 3 times sine 30 degree. And these are going to have both positive and positive direction because it's along the axis direction, right? So if we just do the math, we can find the values for these, right? And VA, oh no, it's VB X1 and VB Y1 is going to be what? The horizontal term is 5, it's cosine, so it's 5 cosine 60 degree, and this is going to be 5 sine 60 degree, right? And here, the polarity of this X version, X component, this guy is going to have a polarity of minus because it's the opposite direction. We define going to the right as my positive, but this guy is going to the left, right? So it has to be a negative value, and if you made a mistake here, then all the following ones may have been a little bit off. And the vertical one, this guy's going up, and going up is my positive direction, so we're just keeping it positive like that. So if you do a little bit of math, these are going to be the values we're looking for, right? So that's the first part. And the second part here is what are the velocity values along the y-axis going up and down this direction of the yellow and green balls right after the collision. And the collision is happening like this, so the horizontal terms are contributing to this collision, but the vertical terms have actually nothing to do with that collision, right? So the velocity before it hits each other is going to be same. You're going to have the same velocity after they hit. So this velocity and that velocity are going to be the same, and this velocity and that velocity are going to be the same. I mean, this is before and here is after the collision. This is going to go up, and probably this is going to go up like that after the collision, right? So the velocity that is vertical to this plane of impact, line of impact, is going to be preserved. So VA Y2, this is after, right? This is before. So after is going to be same as VA Y1, and VBY after is going to be same as VBY before. So you guys can just use these values down there. Okay? And the last part is determine the magnitude and direction of each ball right after this collision. So from here, we're going to use that MV, conservation of MV. So M A V A X1 plus MB VB X1 is going to be MA VA X2 plus MB VB X2. So this is before, so we have the subscripts of 1. This is after, we have the subscripts of 2, right? And this is for particle A, this is for particle B, and we're considering the horizontal terms. So if we do a little bit of math, this is actually they all have same mass, right? So these are all same values, so we can get rid of those, right? And let me copy the numbers that I had. So it's 2.6, this is 1.5, and this is minus 2.5, and this is 4.33, like that. So we have 2.6 from here, and this one is minus 2.5. So minus 2.5, that's critical. If you made a mistake here, then you may have had plus 2.5, which is going to give us something totally different. And this is VAX2 plus VBX2. So this is going to give us 0.1, right? So I have one equation ready, and we can use that restitution coefficient thing. So E is, it's VA, VA, VB, VB, and then this is X2, X2, X1, X1, and it's a minus, right? That's how I kind of remember these. And now we need to plug in some numbers. So from here, E was 0.9, right? And VBX1 is minus 2.5. Minus VAX1 is 2.6. And VAX2 minus VBX2. So VAX2 minus VBX2 has to be 5.1 minus 5.1 times 0.9. So we have another equation ready. And we have two terms, right? And two equations. So if you do a little bit of math, you should be able to get VA X2 is minus 2.245, and VBX2 is 2.345, like that. So we're good now. We got this y terms after collision, we got this x terms after collision. And here it asked us to find the magnitude and direction, so we can maybe draw this thing. So for the A, it's going towards the left, like that, 2.2. And for the y direction, it is going up by 1.5. So this is 1.5, like that. And this is my A. And my B, I have 2.3 something going to the right, and the y direction, it has 433, so like that. So those are the components after the collision, and so the actual velocity has to be this and that, and we can find this angle, call it theta A and theta B. So if I just do it for theta A only, velocity of A is going to be 1.5 squared plus 2.245 squared square root. That's going to be the magnitude. The value should be something like 2.7 meter per second, and tangent theta A is this triangle. It's 1.5 over 2.2, right? 1.5 over 2.2. So theta is a tan of 1.5 over 2.2, which should be something like 33.75 degree. Okay, and you can do the same thing for this VB, and it should give us some value. And obviously, this is going to be a little bit of bigger value than what we got here. Okay? All right, just to summarize these, the important stuff, well, before the collision, we wanted to find out all the velocity components of particle A and particle B along the axis X and Y in this case. And the important thing is, if your velocity has it is towards the different direction, or it's against the direction you defined, then you need to put a minus sign there. Okay, so that's one thing. And the other thing we want to remember is you want to take a look at the cases that you have there, and in our case here, these components are contributing to that collision. These components have nothing to do with that collision, right? So these before and after is going to be conserved. This velocity before and this velocity after, they're going to be the same, right? So the vertical terms in our case are just going to be the same as the ones we had before. Okay, and lastly, we are going to figure out the velocity terms that contributed to this collision. So in our case, the horizontal terms are making these two guys to meet each other, right? So we're just using the horizontal terms, MB, this thing, and we're using this restitution coefficient, and from there we're just doing a little bit of math, right? And after that, we want to find the magnitude and angle by doing these. You can draw these, and then hopefully those are by drawing these, you may have a better idea of what's happening. Okay? All right. Any questions up to here? Okay. Not. Let's move on. And let's try this one here. So this is, again, very similar to what we tried in class. We actually used this figure to find the, what was that? The rotational mass that I call, the moment of inertia. And the pendulum, it has a slender rod, 2 kilogram, this guy, and a circular plate here, 3 kilogram, and it swings clockwise, so it is swinging in this direction, right? So it is swinging like that. And it has, omega is 5 radian per second. And assume gravity is 10, and we want to find the mass moment of inertia of the total pendulum against this point here using the parallel axis theorem. So for the rod, you can find IO is IG plus MD squared, right? And that one, if you take a look at the table that was provided for this guy, we had 112 ml squared, right? Or we can directly just use this one against a point that is at the tip of that rod. If it's swinging like this, then it's 1/3 ml squared. So we can just use that one, 1/3 ml squared. And that should be something like 1/3 of m was 2 kilo, and the length is 2 meter squared, so it's 8/3, and that has to have a value of 2.67 kilogram meter squared, right? And we have the plate, right? And IO again is IG plus MD squared, and IG, let's take a look. For a thin plate, it's 1/2 mr squared, so it's 1/2 m r is 0.5. 0.5 squared plus md squared. So if it were rotating with respect to this point G, right, then it's just this guy, but it is rotating against this point here, right? So the distance is 2 meters and the radius 2, so it's 2.5. So it's m was, again, it's 3 times, oh sorry, this is 3 as well. 3 times the distance is 2.5 squared. And so if we add these together, the IO is going to be 2.67 plus this value, then it should give us something like 21.79 kilogram meter squared. Okay, so that would be the total pendulum IO. Okay, so this is exactly same as what we tried in class, and based on this knowledge, we can try to determine the equation of motions, and in this case, we can try for 2 different directions and have the torque or moment against this point O. So if we draw the free body diagram, we have that rod and we have the pendulum like this, and I can maybe copy this guy, paste it there, and against this point O we have these 2 forces, Nx and Ny, and we can define our axis like NT coordinate system because it's rotating like that. So let's call this as my N direction and this as my T direction, or you can just call it X and Y. It doesn't, let me keep them both here. Or you can call this, oopsie, you can call this X and Y as well. Okay, and this rod has mg, right? And this plate has its own mg. Well, let's call this m1 and let's call this m2, just to be clear, right? And that's all the forces we have, right? And this whole stuff is rotating, so against this mass center G, we have MAGT, and we have MAGN, right? And of course we have this full rotation IO alpha. Right? So from here we can collect the terms, so sigma fx, let's say, and going to the left is my direction, positive direction, and that is going to have only this term, right? So it is minus n of x, and that is going to have mag of t. And this guy has a value of what? Because it's having a pure rotation with respect to this point, it's r alpha. So it's going to be m rg alpha. And sigma f of y, that is going up, is my positive direction. We have ny, right, minus this one and that one, so we can collect m1 plus m2 g, like that. And that's going to be m ag of n, and this term is what? It's r omega squared, right? So m r g omega squared. And by the way, this m here is m1 plus m2. It's the total mass. We assume it is all centered around that mass center. And we are collecting the torques as well. And here we'll just define it's rotating like that. That's our positive direction, because here it was already rotating like this. And against this point O here, there's these forces, right? But none of them are contributing to any rotation here, right? These two forces are just pulling it. These two are just pulling it down as well. It's not making it rotate. So it's going to be 0, and that's IO alpha. So from there, we have these three equations ready for us. Okay? So we have that here. And next, we would like to find the angular acceleration alpha at that instance shown here. What's going to be the value of alpha in this case? It's going to be 0. No matter what value we have here, we actually obtained the value up there, but it's 0 is equal to IO alpha. So from this equation, we have alpha is 0. Okay? So that's just done here. And find the reaction force at point O at that instant. So we would like to find out this NA and NX and NY values. So if we try to find NX, right? NX is coming from here, and NX is minus MRG alpha. And these values, we don't even need to think about it. Alpha, we just found is 0, right? So it's just 0 there, because this is 0, right? Then NY, we need to find it from here, right? And NY is mg plus mrg omega squared, right? M, we know it's the sum of those two masses, so it's 2 and 3, so total is 5. We know it's 5. G is 10 or 9.8. It's 10 here, so we know it's 10. M, I know it's 5. RG, I don't know. Omega, it was given as 5. So RG is all we need to find out. If we know what this value is, then we can get this NY, right? Then we want to find out that RG value. So here we had this fixed at point O, right? And you can think this as you have a mass center here, and you have another mass center there. And this is what? This is 3, no, this is 2 kilo, and this is 3 kilogram, right? So if you had these two particles like that, where's going to be the mass center? It's going to be around here, that has a ratio of 3 against 2, right? So let's say you had like a rod, or let me draw it like this. Say you had a rod like that, and this is 2 kilogram, and this is 3 kilogram, and you're going to put your fingers like that to balance it. Where do you need to put your finger? If you put it here, that has a ratio of 2 to 3, like that, then it's going to be balanced, right? So same thing for here. So now we need to do a little bit of geometry. And so this guy has a length of what? It's 1, and this is again 1, and this is 0.5. Right? So we have this whole thing as 1.5. This thing is 1.5. Then here means 0.9, and this means 0.6. Isn't it? So you have your mass center that is 0.9 meters downwards from the mass center of this point. So here is 1, and you're going down by 0.9. So this point here is going to be the mass center of this overall stuff. Right? So if we plug in 1.9 there, then we can do just math, like 5 times 10, 50, and this is 5, and 5 squared, 125, and times 1.9. So if my math was correct, we get 287.5 Newton, like that. Okay? So just to summarize this problem we had here, we want to first find the mass moment of inertia of this total thing, and we can find those one by one for each, right? And then we can combine those, and you're finding this thing, a rod that is rotating against its tip, and you have a circular plate. It's not rotating against this mass center, but it is rotating around somewhere else, so you need to use that parallel theorem. So from there we can find out this value. And next it asked us to find this equation of motion in F equals ma in 2 directions, and this against 0.0, right? So we're just drawing the free body diagram and collecting all the force along those 2 directions, and if it's against the positive direction we defined, then those are going to be minus values, something like these. And none of these forces are contributing to the rotation against this 0.0, so here it's 0 is I alpha. So from here we got alpha 0. From there we can find nx is 0, and ny, it involved a little bit of math, right? But all the terms were provided. Just this guy we had to find out. And the mass center of this overall thing, you can consider this guy is centered here, this guy is centered there, 2 and 3. So you can think there's a rod with 2 kilo and 3 kilo there, and you're putting your finger to find the point where it balances, right? Then it's just this ratio. So from there we can find out this point, which is 0.9 meter away from the mass center here. So it's total 1.9 from this 0.0. Okay? All right. Any questions? Okay. None. Let's move on. And let's try this last one here. So there was this 50 kilogram cylinder shown right rolling, yet you do not know whether it's slipping or not. And the kinetic and static friction coefficients are provided like that. So first it asks us to draw the free body diagram of this system. So that's relatively simple. So we have the circle there, and we have some forces. So of course always we have mg, and because it's touching the floor, it has the normal force like that, and it had some external force P that was being applied, and we can have some whatever friction force like that. All right, so we're done with this. For the friction, you can draw in this direction as well. It doesn't really matter, okay? Later when we do the math, if this turns out to be a negative value, then it means it's just pointing that direction, okay? But these are the terms that you want to find out. And then find the equation of motion for this system, such as these and IO alpha, these types. So here, if we define its x and y like that, then sigma f of x going to the right is my positive, is going to be what? We have this term and that term in the horizontal directions. So its p is 200, so it's positive 200 minus f going to the left side, and that is going to be mag of x. Right? And sigma f of y going up is my positive, so it'd have n minus mg, and this is going to be basically 0. All right? And sigma m against point O was here, right? So against this point O here, and I'll assume this is my positive direction, and in this case it's going to be what? This force is making it rotate, but these three forces are not contributing to rotation against this point O, right? These are just pulling this point, and this guy is pushing this point, so it's not making it rotate. Only this guy is making it rotate. So 200, this was 200, right? 200 times this length, which is 0.3 meter. That's the only torque that is making it rotate, and that's going to be IO alpha. Right? So in this case, one of the easy ways to solve this thing is we want to assume it's rolling without slip, right? So if we do that, AG becomes what? R alpha. So we can plug this thing inside here, so it's going to be M R alpha. So that's one thing, right? And from here, if we write this thing again, 200 minus F is MR alpha, where M is 50, R is 0.3, and alpha is, I don't know, right? So this is 15 alpha. And N is mg, right? That's easy. So M is what? It's 50 kilogram again. And G, it's not specified, so we can just use 9.8, something like that, right? And the last term here is 200 times 0.3, so it's 60 is IO alpha. So we need to find out IO. So IO is IG plus MD squared. And in this case, we have this cylinder rolling. If it was rolling against its mass center, then we have it there, and we can cheat from here. It's again this cylinder, so it's 1/2 mr squared, right? So it's 1/2 what's my m? Is 50, r is 0.3 squared plus md squared. In this case is again 50, and d squared is 0.3 squared. So right, and that's going to be, I don't have the value here written, it's just 1/2 and yeah. So we can plug this thing in there to find out that IO we just found out here, alpha, and from here we may be able to get our alpha is 8.89 radian per second squared if my math was correct. Okay? So yeah, by doing that we found the angular acceleration. On the other hand, it also asks us to verify whether it is slipping or not. So we assumed it was slipping. It was not slipping, right? But we need to verify that. The way we verify it is F has to be smaller than the static friction, the max friction force. So we need to find out this guy, and we need to find out this one. So F is obtained from here. Therefore, we can find F is 200. We move this thing to the left and move this to the right. And it's 200 minus 15 times alpha, right? And that should be something like 66.7 Newton. So it's 66.7. And this whole term is mu s is 0.2, and the normal force is 50 times 9.8. So this is like, what? This is 10, right? 10 times 9.8, so it's 98. And from here we see 66.7 is smaller than 98. Therefore, yes, it meets our condition. So it's verified that our assumption was correct. Okay? All right. Any questions up to here? All right.